Let's look at the third example, that in which we have the water has to be discharged at the ratio, specific ratio of the discharge of the 1.8 cubic meters per second from a large storm water detention tank into the sea. You can see through via a submerged outfall. So we can have like an outfall, submerged outfall pipeline. And the pipes have a friction factor of the lambda of 0.04, and the entrance to the sea has got like 130 meters long pipeline, which is sharp. So we have like the entrance is sharp. So we have like a minor head loss in here, and the length of the pipe is 130 meters. The length of that, you need to just consider like a friction head loss formula. So the question here is to calculate the elevation of the water surface in the detention tank above the sea level required to obtain the necessary discharge if the pipeline is constructed with a uniform diameter of either 0.9 meters or 1.2 meters. So the question here is that what is the level, water surface level, that we need to make sure, for example, where do we need to just construct, or where, or what is like the water surface level that we need to just obtain to just make sure that we should be able to discharge this amount of the flow through this kind of like the pipeline to the sea. So that is the question. So if it's like very close to like a sea level, we may not be able to discharge this. And bear in mind, we have like a pipeline system, and we have a friction head loss happens, and we have an entrance. So we have an entrance head loss, friction head loss, and we need to just see what other like the head losses that we have. So if we're just gonna use the Bernoulli's equation between like a point in the water level in here, water level in the sea, and the water surface at the like the top of the reservoir, we can just use again, we can just cancel out or remove the pressure head and also the velocity head, because they're just gonna be zero. We don't have that one. As a result of that, if the reference line is chosen as here, this point, we only have the elevation head for on the left-hand side, which is like the Z. On the right-hand side, all the elevation head, pressure head, and velocity head are zero, and the only terms left are all the energy head losses that we have. One term, entrance loss, then second, friction loss, and also exit loss. We learned from the previous examples that the entrance loss is a half times V squared, V like the velocity in the pipe, squared over 2G. Friction loss is lambda L V squared over 2GD. And the exit loss is a one time V squared over 2G. So with that assumption, or with that kind of like the simplification, we can easily substitute the value because we have all the terms here. And once we're just gonna calculate with the like the diameter of the 0.5, and second, we're just gonna calculate with the diameter of the 1.2. And we have the lambda, we have the L is like 130, lambda is on 0.04. And the only thing that we don't have it is like the velocity. So the velocity, but we have like a discharge, and we have the diameter, either this value, or the second one. We can easily, by using the continuity equation, we can calculate the velocity as well. So we're just gonna first step where for like the assumption of the pipe like the 0.9 meters diameter, we're just gonna calculate by using the continuity equation. We're just gonna calculate the velocity. So if we just use a continuity equation here, the velocity is calculated by rearranging this formula. Is like the discharge is like the 1.8 meters divided by A, area, cross-sectional area is like a pi, times 0.9 squared over 4. So the result of this is like a 2.829 meters per second, so almost 3 meters per second. So we're just going to use in this equation, which substitute in this equation, we have the velocity. We can easily calculate the unknown variables, which is the Z that is required. So we're just going to put it here for the first term. We have 3 terms here, half times V squared over 2G like the 19.62. Second one is a lambda 0.0404 times 130 times 2.829 and squared over 19.62 2 times divided also by 0.9. Just bear in mind, this is like the denominator is a diameter here. And plus the third term is like a v squared, 2.829 squared over 19.62 is a 2g. So the result of these 3 terms together is equal to 2.969 meters. Almost we can say 3 meters. So it needs, if you have like a diameter of 0.9 meters, like less than 1 meter, you can intuitively imagine. We need to just have the water surface around 3 meters above the maximum sea level. So if you have that one, you will make sure that the flow discharge of 1.8 cubic meters per second will be guaranteed and will happen. So we have that with this kind of like the diameter. Let's look at the second assumptions. If you're just going to increase a pipe of the size of like a 1.2 meters, what would happen? So we change like a 1.2 meters of the diameter of the pipe. We repeat the procedure. First of all, we calculate the velocity is equal to 1.592 meters per second by using the continuity equation. You can see it's like the half times of the velocity. Okay, let's see if we can just get the different value for the Z and how much different it is. You know, the velocity has not been increased by twice, but it's like what we can see the velocity decreased by almost like 50% of the original one. So if we're just going to substitute the right-hand side formula, you can have like the Z again for the 3 terms. The only difference is that the velocity is this time is like the 1.9452 in here. So if you're just going to sum up all the 3 terms here, the Z eventually or the water level that you need to obtain or need to provide to just make sure 1.8 cubic meters per second is provided or happens is equal to 0.754 meters. Just compare these values like almost like the 0.8 meters. 0.8 meters compared to 3 meters, you can see something around like 4 times smaller than this, 4 times smaller than this. By increasing the size of the pipe from the 0.9 to 1.2 meters, you can easily reduce the water level required to just discharge this amount of the flow. And you can see here, and we can say with the diameter of the 1.2 meters, the minor head losses comprises 26 meters of the total head losses. And we can achieve these sort of things. I mean, if you're just going to look at all the 3 terms, it might just give you a better a breakdown and better the understanding about what has happened. So you can see here the increasing the diameter. You can see here the main term here is a friction head loss. The second term is like a 2.4, but you can reduce that one to almost 6. You know, it's something around like 4 times smaller. The other the first term and the third term, there are also decreases as well, but because in the original formula, the proportion of the minor head loss entrance and exit are both of them are really small. Although they just decreased 4 times smaller, but their contribution are not so much significant. But the friction head losses reduction 4 times is really significant and can have an impact on the total Z required for this discharge or for this problem. This is the third example of the friction and the head losses.